Welcome to our afternoon session. It is my pleasure here to introduce Patrizia Rossi. We'll talk about some physics at 22 GeV, what we might be able, what we would like to do with the upgrade that we learned about yesterday. And I've known Patrizia for 20 years, perhaps. Yes, when I was doing electron nucleus collisions in hadronization, and I was visiting Frascati laboratories, and then we crossed paths many times since then. And now we are colleagues here at Jefferson Lab. So before we start, this too bad it's being recorded, but we have a social after at 4:30. Without rush, please come at the residence facility. There will be light refreshment. We can chat, get to know each other. We can talk about physics, life, the meaning of everything, or soccer. There is a European Championship coming up, and all that. So please join us at the social after the two lectures. After you exhaust all your questions, she's ready to answer them. And after that, we can relax at the social. So, Patrizia.
Thank you. Thank you very much. And I'm really happy to be here to talk with you. I want first to clarify something because they gave me this title now and in the future. My presentation is not just the future of Jefferson Lab, what we are planning for the upgrade, but I mix this, what we are doing now and what we can do with upgrade for the same topics. So I didn't want to divide, but I divided by themes, by topics, not by energy. I thought it was, maybe it's more understandable. This is the first thing. The second thing is that I understood that you have a different background. You are a theorist, experimentalist, different level of education. So I try to be simple, at least in the introduction, so you can understand what we are doing here in a simple way and then present some results. And okay, and then you ask me if you don't understand, if it's not clear, if you need more clarification. So in order to understand what we are doing here, I start with a simple slide. What is the JLab's mission? We have two main topics here of study. One is to gain a deeper understanding of the structure of matter. And this is the majority of our experimental program. And the other is the search for physics beyond the standard model. You know that the visible universe is only 4–5% the visible matters of all the dark matter and dark energy. But it's very important. Even if it's a small fraction, a small percentage, it's very important. It's very important that we understand where are we from, what is all around us. And we know I put here this very simple picture which represents the human being in the universe, visible universe. And at the end, what everything that is visible made of is made of atoms. Atoms, you know, as a nucleus, proton, neutron, electrons flying around. But the proton and neutrons are not elementary particles. Inside the proton and neutrons, we have the quarks and the gluons. And this is the physics here at JLab, the physics of quarks and gluons. So just very snapshot of the excursus that the human being did in order to go to these quarks and gluons. Maybe you have seen this slide many times. We start from the atomic hypothesis with Greek 100 years ago. And here I put the scale. Each time that you go deeper in our understanding, our scale of investigation is smaller and smaller. So we start with the visible eye, 10 to the minus 4 meter, 10th of a millimeter. And then there was a big jump. We have to arrive to the 16th, 17th century with the chemistry to jump of 5 orders of magnitudes in scale for a deeper understanding of the matter. And we have this, the molecular theory. And after that, we have a beautiful table, is the periodic table of elements. All the elements are organized based on their Z their atomic numbers. And it was really a great classification. We start to put order in our universe. After that, there was in the 19th century, really it was a jump of our understanding. We went to the discovery of the atom as a nucleus, and this was a major discovery. And our scale now is the order of 10 to the minus 16 meter, 14 meters, sorry. And then the discovery of the neutrons, 10 to the minus 15 meters. Finally, we start to see and have the evidence of the fact that the proton is not an elementary particle. We had already have this evidence with the fact that the proton has a magnetic moment which is not unit, but here we have with the proton form factor in the 60, end of the 50, beginning of 60, we saw that the proton is not a point-like particles. And then finally we went to the quark, 10 to the minus 18 meter. So we have the discovery, the evidence of quarks, and I will go back to this picture. And at the end here we have, you see here, this is the classification of all the elementary particles in the universe and the interaction of the 3 of the 4 forces which act to these particles. And you see we have a beautiful classification. We went from this periodic table to this other classification. In this periodic table, we have the 6 quarks, we have the leptons, and we have the carriers of the forces. And here at JLab, we studied this, the interaction of the quarks, and we are using so the dynamics of the quarks, which is the quantum chromodynamics, QCD, which is one of the pillars of the standard model. And we have gluons, which are the carriers of the strong force, the force which act among the quarks. And we use, for this investigation, electrons, real photon also, and for some experiment also Z-particle enter into the games. But I'm not going to talk about the part in which we use the Z-particles. That said, how would you know all of this? And for this, we really exploit the power of the charge particle scattering, the scattering process. What's the scattering process? It's very simple. Each time that we open our eyes, we do a scattering experiment. We have light, bounce off an object, the object hit our eyes, and then our computer, our brain, reconstruct the image. And this is the same what Rutherford, for instance, did to discover the nucleus. So he used these alpha particles passing through a foil, a thin golden foil. He saw that the majority of the time, these particles went through without any deflection. But for few events, they had a big deflection. This was the scattering. So the alpha particle was scattering off something dense, let's say. We also know that to each particle, we have an associated de Broglie wavelength, okay? And this wavelength, and all particles have all these properties. We have this duality property, particles wave. And a particle can probe, having this wavelength, distances which are of the order of the particle's wavelengths. So almost all particle physics experiments today use the same basic elements: a beam, a target, and a detector, okay? Now, I introduce you the 2 main experiment type of scattering that we are using. One is the elastic scattering, and with the elastic scattering, we use, here at JLab use electron as a probe, or photon, as I told you. And the electrons in the elastic scattering bounces off the proton as a whole. So the proton is not destroyed. But we do also a lot of experiments, actually the majority, the so-called deep inelastic scattering. What is this? The electrons, or the electron, bounces into the proton and then scatter off the proton's internal part. So the proton is not anymore, is destroyed at the end. It's not anymore intact. And so the electrons bounce off the internal part of what we found internally of the proton. And this is the two major categories of our experiment: electron scattering, elastic scattering, and deep inelastic scattering. Let's now introduce the deep inelastic scattering and the important variables that you are going to hear during this talk. So you are going to hear about the x, q square. What are these variables? So, and I put here the first the experiments at SLAC. They found the evidence of the quark. This was, they used an electron beam of 20 GeV, very high energy, hit a proton particle, and at the end, they detect only the scattering electron. And the kinematics for this process is the following. So in the initial state, I have the electrons with the form momentum k, which means energy E and k vector for the momentum. And the same for the scattering electron. The wavelength is really, and then I have this reaction goes through the exchange of a virtual photon, gamma star. And this gamma star has an energy nu, which is the difference between the incoming and the outgoing electrons, and as a q, which is again the difference of the form momentum k and a q vector. And the important variable is q square, which is the difference of the form momentum of the electrons. And the wavelength that I'm going to use to probe the internal part of my particle is related to q square by this relation. So higher is q square, smaller is wavelength. In the final state, you're going also to listen about W, which is the invariant mass the invariant mass of the final states. And you see here, if I have an elastic scattering, my W square is equal to M square, because Q square is equal to 0, nu is equal 0, E minus E prime. So I have W square is M square. What have they found in this experiment at SLAC? This is the cross-section of my experiment, and you know what is I assume that you know what is a cross-section, right? It's a probability, gives us the probability that there is an interaction of the particle with my target, okay? They found that they measured this cross-section, so this probability versus Q square, the transverse momentum, the momentum transfer, the square of the momentum transfer. And they found the following. You see that this is the cross-section of the elastic scattering. So if my proton is intact, then the cross-section goes rapidly down with the Q square. In this case, they found that higher was the W, so higher was the energy, and more flat, actually, the cross-section didn't depend on Q square. It was invariant, right? What does it mean, this? That actually the scattering was of a point-like particle, a particle without a form factor, without a distribution, because the form factors give me the information about the distribution of charge magnetization of the particle. And this was the evidence of the quark. Why the experimental evidence of the quark? They actually call this parton, not quark. Quark was introduced even before this experiment to organize the particle zoo and by Gell-Mann. And they thought actually at the beginning it was assumed that it was just an artificial, mathematical artificial to give for the organization of these particles. But at the end, the experiment proved that the partons that they saw in this experiment were actually the quarks with a spin 1/2. I cannot go through all the details of this, but believe me, it's this. So how then, I have to introduce now this parton model. I told you about this parton. They said these are parton. These are elementary particle. To introduce the parton model, I have to introduce the infinite momentum frame. So how this experiment here can be described, and it was described in this way. So I assume that the proton is fast moving in one direction, and the particle inside the proton, they are almost free. And the interaction of the gamma star is with this elementary particle inside the proton, which moves collinearly with the proton, and they are free because the interaction, so the proton is moving very, very fast. So the time is dilating, and practically the quarks, the partons, they don't interact each other. Now, in this description, each parton, which has charge EI, has a probability Fi to carry a fraction x of the parent proton momentum. And this can be, I use this picture from a talk by a colleague, which I found really great to describe this parton distribution function. Assume that your proton is this ball filled with water, and inside the ball you have this fish. And this ball is on the skateboard. Okay, so the skateboard and the ball is the proton moved on the skateboard with some momentum. And then you measure the fraction of the momentum that each fish has. And you repeat these measurements several times, and you have this distribution. You find that at n time, for instance, you have n fish that has 0.2 fraction of the momentum of the proton, 0.4, and so on and so forth. And you have this distribution. So the cross-section then, you can describe the cross-section of the process as I can factorize the cross-section with an elementary particle, a cross-section on the elementary particle, the quark, times a function of the internal structure of my proton, which is described by these two structure functions, F1 and F2. And F1 and F2 are related by this relation, and they depend on they are function of this probability Fi. So the structure function Fi, the x, is the probability to find the quark with a fraction x of the proton momentum. And this is this x, this fraction, is defined by this quantity, q squared divided 2m nu. And this is the so-called Bjorken variable. I insist on this because you see, these are the variables that we are using here for our experiment. Now, if I go, what's happened if I increase the energy? So with the 22 GeV electron, we saw in the experiment the quarks. So how the shape of the proton depends on this x, on this variable x. So if I have a closer look inside the proton, I see the following. At a certain x, 0.3, I see that the proton, this is the image of the proton. I can see that the proton is made by 3 valence quarks, UUD. You all know this, right? The property of the quarks are defined, the proton are defined by this valence quark, UUD. But as soon as I increase the energy, So I go deeper and deeper in X. X is Q squared divided 2m nu. I see more and more quarks and anti-quarks popping up and created by the splitting also of the gluons which interact that are the carriers of the strong force. And more I go down in X and I see more and more gluons. And this is how these parton distribution functions F behaves versus X. This is the behavior of the parton distribution function versus X. And you see here that in the valence region, X.3 more or less, I have 2 U quark and 1 D quark. And more and more I go to lower X, I see the increase of the gluons, more and more gluons appear, and the increase of these C quarks. Now, the long distance physics, which is this one, X03, valence region, and the parton pictures, when I go down and down, I see more and more these partons. Both long distance and short distance are described by the QCD, which is the fundamental theory of the strong interactions. And this year is the 50th anniversary of the QCD, let's say, discovery of QCD. I put here, there is a nice paper, more than 600 pages, which summarized the history, how the QCD evolved, and all the problem that physicists had in order to have a coherent picture of the strong force. Now, what are the, I want to give you some basic information on the main information of QCD, how QCD works, which is completely different from QAD. You see, when you have an electromagnetic interaction, longer you go from the source of your the charged particles, and less you feel the field of the electric field. For the QCD, for the strong force, we have this behavior which complicates our life. So there are, first of all, the quantum field of the strong force is a colored field. So when we talk about QCD, quantum chromodynamics, we introduce a new quantum number, the color. And this color is carried by quarks and gluons. And this is the big complication of the QCD, because gluons interact with each other. In the electrodynamics, you have the photon, which are the carriers of the electromagnetic force, but the photons, they don't carry charge, so they don't interact with each other. This is not the case of the gluons. And this is a huge complication. If I see the alpha strong, the coupling constant of the strong force, this is the behavior. This alpha strong is very small at very small distances, while it increased a lot when I go to large distances, the distance of the atomic nucleus, for instance. What does it mean, this? This means that in this region, which is the asymptotic freedom, in this asymptotic freedom, I can apply the perturbative QCD to solve my Lagrangian. And you see here the Lagrangian of the QCD is quite simple. The problem is that there is this terms, which is the gluon-gluon interaction. So here, the perturbative QCD, I can apply the perturbation theory, because here the quarks move as thought they are free, no interaction. And we tested the perturbative QCD up to 1% level, very precisely. Here, I cannot solve the QCD from first principle. And here we have an important feature of QCD, which is the confinement. What is the confinement? The confinement is that if I try to pull out a quark from the anhadron, I cannot. The energy that I use to pull out this quark, it's enough to create another quark-anti-quark pair. I can never see a free quark. This is the confinement. And this is a $1 million price if we try to solve analytically the equation at a large in the confinement. Confinement is not solved yet. So we have this alpha, which is this coupling constant, which highly depends on the energy scale. Now, so we have color for the QCD. We have introduced the color. We have this coupling constant, which depends on the energy scale. And the other important feature is that QCD, there is this factorization theorem that helps us in a certain sense. What does it mean? That for a wide class of physical quantities, for instance, the inclusive cross-section, the one that I show you the experimental slack, can be the cross-section can be factorized into a long-distance component, which is not calculable, but universal, F1, F2. And the short-distance component, which depends on the process, but is calculable, okay? And actually, this is a success of QCD. We had the proof that we proved that there is a success of QCD and QCD factorization. Those are the F2 structure functions measured at a different x. You see the spanning x from 0.65 up to 0.000102, a large range in x, and also a large range in q square, 5 orders of magnitudes. And the structure function F1 that was extracted from here, F2, were used to predict the cross-section for other processes. For instance, electron-proton at 0.3 TeV, or proton-antiproton at different TeV energies. So we could extract the F2. F2 depends on the property of the proton. So it's universal. Is the elementary cross-section, which depends on the specific process that I'm going to measure. Now, this is my favorite slide, my favorite pictures that gives you, this is the QCD. The beauty and the beast. It's a beast, but it's fascinating. It's fascinating is the highly non-perturbative behavior that makes the study of QCD so fascinating, at the same time, so challenging. And I found that this paper written by Bjorken, which actually said is the non-perturbative QCD is the most interesting and the most important portion of QCD to address, despite the evident difficulty in doing so. And here at JLab, we study QCD in the non-perturbative regime. It's a critical lab to have a deeper understanding on the structure of the matter. Now, so you understood now that we were very successful in starting from the matter and going down to pin down quarks and gluons. But we didn't succeed yet in the inverse path, because we don't have a detailed understanding of the way QCD generates protons, neutrons, and other strongly interacting hadrons, which remain this process elusive, still elusive. Okay, it's the emergent phenomena that we don't understand yet. How from quark and gluons we have the emergence of the matter around us. Now, what are the most challenging questions that we are addressing here at Jefferson Lab? There are many, but these are, let's say, I couldn't do all the list of the questions, but the most important are this one. So, first of all, how the microscopic properties of the nucleon, mass, spin, you know all about mass spin, you have heard about the mass spin of the nucleon, emerged from QCD. There was the so-called spin crisis. If you sum up the spin of the proton, the quarks in the proton, you don't have 1.5. It's 30%. 25%. Quarks contribute to 25% to the spin of the proton. What is the missing spin? Where the missing spin comes from? Now, how the fundamental particles, quark and gluons, fit together, interact to create a different type of matter in the universe? We have many particles. Why the majority of the observed hadrons fall into only two very limited sets, the baryons, 3 quarks, or the meson, quarks anti-quark? What is the role of the gluonic excitation in the spectroscopy of this light meson? What is the relation? And if we move from the proton to the proton in nuclei, what is the relation of the short-range nuclear structure and the parton dynamics? At a certain point, all the nuclei are made of proton and neutron, but those proton and neutrons are made of quarks. So how from quarks I go to hadrons and nuclei? And I know that I can describe nuclei in using a certain theory, but I'm not yet able to describe the behavior of nuclei using quark and gluons. And what is the relation of the short-range nuclear structure and the parton dynamics? Exactly. What is the hadronization mechanism? Because as I said, I cannot pull out a quark from a proton or from a nuclear structure. But in the final states, when I do my experiment, I have many particles. How this happens? How I can create this particle? How the particles are created? What is the force which is entering into the game? In which way? Is fascinating. So we try to answer all these questions and more in this lab. So, and here, this is me when I try to summarize, prepare these slides for you. So here, really, we have many experiments, many interesting results that I would like to show to you, but I can present only a few of them. And I was thinking, okay, what is the best way to present all these results that we have, all these fascinating things that we are studying? Why we have many things, many observable? Because this is a proton, okay, we study the proton attacking from different parts. We study the form factors, as I said, gives the information about the distribution of charge and magnetization of the proton and neutron, and nuclei as well. But, and so we study the parton distribution function, how it is distributed, the momentum of the proton among the constituents. But we study this parton distribution function. Now we try also to do in 3-dimensional, not just 1-dimensional. I show you the parton model, it was just 1 dimension along X. What is the spectrum? You know that there is an important part of the program at this lab is the spectroscopy. So you excited a proton, you have you create exciting state that decay, and how this spectrum emerge from the excitation of the spectrum, how this excitation is created, what are the information that we can take from this study. And also, of course, nucleons and nuclei. So all these pieces, that's why I put on top of the proton, these puzzles are pieces that we want to put together and to connect the dots at the end from all this information, which is incredibly difficult. So here at Jefferson Lab, we are exploring the different facets of the non-perturbative dynamics that manifest in hadron structure. There are multiple observable, and all these observable are sensitive to different characteristics of the hadron, of the nuclear structure. Each one is more sensitive. Each of these is specifically sensitive to some aspect, okay? And you can imagine that these studies requires really precise measurements. This is critical to have precise measurement. And you know, to have precise measurement, what do you have? High luminosity of your accelerator, of your experiment. So this is just a slide to show you how we portioned all this study in the different categories. This is the pie chart. You see that half of our program, this is the program that we have already approved for the 22 GV. We have more 125 experiments on our book, and we already took data for half of them, 50% more or less. We still have 50% of the experiment to run. And we have, you see, the orange part is the nuclear structure. Then we have nuclear part, which is the gray, which is then the hadron spectra is the blue. And then there is this portion also, which is the study of the physics beyond the standard model. You see, is quite sizable. As I said, we already run 50%, but the approved program equals well beyond a decade. We still have a decade for the approved experiment, but every year at JLab, we have the program advisory committee and people submit the proposal, their experiment that they want to run here. And so this is for sure, we are very busy here, no doubt. And we have all this program is supported by a vibrant user community. Here at JLab, we have 1,900 users coming from all around the world to do experiment here. About CBAF, yesterday you have already had a lecture on that. I will summarize here only a few points that this is a high intensity beam. It's a continuous beam, electrons. We have electrons, but we have also in one experiment, this beam is sent simultaneously to 4 experimental holes, A, B, C, and D. And in one of these holes, we have linearly polarized real photon, not virtual, not the gamma star, the real photon, the photon for which Q square is equal to 0. It's highly polarized, and this is very important. And you see here, this is very, very important. Here at this lab, we run fixed target experiment in all holes. We don't have a colliding beam. Here we have a fixed target experiment, and we run this experiment at very high luminosity. Here is JLab compared to other EP facility in the world. And you see that is, for instance, compared to AAC, is for 5 order of magnitudes. It means that if you need 1 day to run an experiment here, you need 100,000 days in a facility in which the luminosity is 5 order of magnitudes lower. And this is the excursus of this CBAF. We started this 40 years ago, more or less. The 4 GV, we went immediately to, after a few years, to 6 GV. And then in 2015, we doubled the energy and we went to 12 GV. And this is very important, this jump. You see here, in the up to 6 GV, we could investigate the structure of the quark. We know that we have 6 quarks in total, I showed you in my initial slide. And UDS, we were able to study matter made by only these light quarks, UDS, because the strange quark is the energy of the strange quark is 100 MeV. When we went to 12 GeV, immediately there was a jump, and we could reach the energy to study the Chan quark, which has an energy of 1.3 GeV. You see 1 order of magnitude here, heavy quarks. And I will show you what important information we got by studying the Chan quark. Okay, we have 4 experimental holes. In these experimental holes, we have detectors. And these detectors, they are complementary among the 4 experimental holes. We have in all B and D large acceptance spectrometer. It means that with this detector, in all B is class 12, the name of the spectrometers, in D is blue X spectrometer, we are able almost to detect all particles in the finite states, because we have almost, not 4 pi, but it's a large acceptance. We can measure particles from our scattering experiment at a large angle, also detected at a large angle. In all A and C, we have a more conventional spectrometers. And conventional spectrometers, you have usually a small solid angle, you have a tiny phase space that you can access, but you can run a much higher luminosity. And this is in the whole A and C. And with a thick line, I highlighted the detectors that we are now using, for instance, in all C, in addition to the initial two high momentum resolution spectrometers, now we put also a spectrometer to measure the neutral particle in the final state. And with these other lines is what we are going to, we have in the plan to study in the future. Is in OLA, we have this smaller experiment to study mainly physics beyond the standard model, and which is under construction, there is another large acceptance spectrometer solid, which want to bring into project. We have in all C, we are going to set up an experimental apparatus to study hypernuclei. And in all D, actually, we try to also generate a new beamline with a kaon. What is the planning for the future? You have already, yesterday, you have heard about the technical part of this. So I will not go to the technical part. You know that there are two arcs that we replace, a new injector. We will be able in this way to double the energy to almost 22 GeV, passing by using, making the beam going through these arcs several times, and with the different energies. But this is the main part of what we want to do with the 22 GeV. What is the plus for our physics program? And the plus is this: we will have a new territory to explore, okay? We will have much more state with the charm quartz, charm and the anti-charm quartz to study, and also with the additional light quarks, so more heavy matter to study because we have higher energy. We have a better insight into our program, and I will show why. If you have higher energy, you have higher Q square, you can study the evolution, for instance, of the structural functions. And it's important to have a bridge between what we are doing now at JLab and what is planning for the future. You have heard about the ESC. There will be a lecture about the electron-ion collider that will be built at Brookhaven, which is under construction. The detector is under construction. The project is under development. And the goal of ESC is mainly to study the gluons. Is the machine to study the gluons, very low X. While the focus of this lab is to study the valence quark, the valence region. And having an energy that goes up in energy, a machine that double the energy, is you will see the trend of how the characteristic of the matter can change with the energy. And the important thing is that, of course, this program will take advantages of the high luminosity of JLab, but we don't have to build new detectors. It's just an upgrade of the accelerator. And part of the future program is also positron beam, and that I will not touch in my talk because you have already heard yesterday, you had the lecture on the positron beam. Now, I want to give you some hints of what we did, some measurements. I don't know if I have to stop now because it's, Oh, very well. This is a surprise. I thought 1:15 because 2:15 because I started 1:30. No, I can go, no problem. I was trying to rush because I thought I couldn't have time to show 10 minutes. Okay, I'm fast, usually I'm fast. Okay, so let's start with the structure of the hadron, the proton. What we learn what we learn with the 6 GeV, 12 GeV, and what we can learn with the 22 GeV. What is the big change that we can have in the information that we can have with the 22 GeV beam? Okay, all the properties of a proton. You think about the mass, you think about the spin, you think about the electric and magnetic charge. All comes from what? The dynamics of the quarks and gluons, obvious, right? But in which way? This is the main problem. We don't know in which way. Okay, let's start with the simplest stuff, which is and I hope that everybody in this room knows about the or at least I've heard about the electromagnetic form factor of the proton, which is more than 60 years that we are studying this in order to understand the property of the proton and the neutron, let's say the nucleon. So in which way we study the electromagnetic form factors? As I said, it gives us the information about the distribution of, in simple words, charge and magnetization of the proton and the neutron. We use the elastic scattering because we want to see the proton as a whole. We don't want to destroy the proton. We don't want to see what is inside. We want to see just the distribution of charge and magnetization. Oops, yes, it's here. So you use elastic scattering. And this is, let's say, how the process, we can express the cross-section in terms of these two form factors, the Dirac and Pauli form factors. The Dirac is conserve the helicity, and the Pauli is instead is the helicity flip form factor. When we do the experiment, in order to measure the form factors, actually we don't measure F1 and F2, but we measure G and GM, which is related to F1 and F2 by these two expressions. And we express the cross-section in terms of the Rosenbluth formula. Okay, what is the cross-section? It's the cross-section of the MOT. It means the cross-section of point-like particle, sigma m, times this expression, which depends on this form factor, G and GM, and on the scattering angle, theta, through this expression. Then there is this tau variable, which is, you see here, the Q square. Q square is always there in our experiment. Now, what we have learned in these last 60 years of doing all these experiments on the form factors at a different Q square, so a different energy. This is what if we do this, as I said, the cross-section, we can express the cross-section in this way. And then we can rewrite this expression having this reduced cross-section. Why I rewrite the cross-section in this way? Because if I measure the cross-section at fixed Q square, at a difference epsilon, so moving theta A, I can put my points, you see, this is a linear relation between G and GM. So if I measure the angular dependence, theta, of the cross-section at fixed Q square, and the epsilon dependence of this cross-section reduced, sigma r, is linear with the slope G square and the intercept tau GM square. And the results that we knew for 40 years is that this ratio, G over GM times mu, magnetic moment of the proton, is equal 1. For 40 years, we believed this. In 2000, here in this lab, we did an important experiment, and after that, many others that show that this ratio is not equal 1. And we could, and in which way we did this experiment? Measuring directly the ratio. We didn't extract this ratio G over GM from the slope and the intercept of the line. We measure directly G over Gm with the polarization transfer. We measure the polarization of the electron, incoming electron. We measure the polarization of the proton in the final state, longitudinal and transverse polarization. And from this direct measurement, we saw that this is not true, that this is one. And why we could do this? Because polarization measurement, we need a very, very, very high luminosity. And you can do this only with a high luminosity machine. Now, of course, this was really a striking result. Finish? Oh, okay. Then, okay. Break, and then we'll tell you what we are doing with the 12 GeV and the future.
Okay, this might be a silly question, but my research involves X being the transverse momentum fraction. I'm just kind of curious if the Bjorken X is at all related to that, or if there's kind of some naming convention between the two, between the Bjorken X and transverse momentum fraction X.
Transverse momentum fraction X. What is that transverse momentum?
It's
what kind of experiment are you doing?
This is a particle collision. When you strike a hadron with some particle and then produce a jet of more hadrons and mesons, and then yes, the momentum of that jet, longitudinal or transversal.
But is it transverse momentum then, not transverse X?
It's well.
The PT.
Sorry?
I never heard about the transverse X Bjorken. I don't know, Alberto, if you heard about the transverse X Bjorken. Maybe you are talking about the transverse momentum of the particle from the jet.
Yes.
Okay. Yes, there is a link in TP collision. For sure, there is this link. I cannot show here, but yes, in fact, when I'm going to talk about TMDs, transverse momentum dependent distribution function, also with the jet, you can access that. Now I don't have the exact relation between X Bjorken and, but yes, of course, they are linked. But it's transverse momentum. So X is a fraction of a longitudinal momentum. PT is the transverse momentum, but it's, yes. I mean, I will show you that in TMDs, you have X, your variables is X and PT.
Right.
Yes.
Well, the connection in the jet is more with the fragmentation functions. So like you have the longitudinal momentum fraction of a parton inside the proton, right? When you have a quark which has been struck out by the collision and now has to dress itself with some other quarks to form other hadrons because of confinement. Now, you can describe this hadronization process, that at least for the leading hadrons, the hadrons that have the largest energy, as being formed out of this quark. So you have a fraction, two things, longitudinal momentum fraction of the hadron that is produced by the quark, and that is usually called Z. And then you can also think about the transverse momentum of the hadron compared to the direction of motion of the original quark. So they are analogous concepts, not exactly the same thing. And the other way that the X connects to the PP collisions, for example, is when you have the proton-proton collisions at high energy is due to the collision of one quark of momentum fraction x1 from one proton against a quark of momentum fraction x2 from the other proton. And these momentum fractions are what are probed in deep inelastic scattering, and in particular by this Bjorken variable XB. So if you do a calculation in leading order in QCD, X Bjorken, defined as in the table that we had before, is equal to the momentum fraction of the quark inside. Okay?
Okay, thank you.
It's more or less what, so when, for instance, we are going to study these TMDs for not a jet, but with the deep inelastic scattering on a proton in the final state. So you have, as I said, in deep inelastic scattering, you measure the scattered electron and also one, for instance, pion in the final states. And this involves the hadronization of the pion. And we measure the transverse momentum, PT, of this particle. And this PT is linked to the internal KT of the quark, transverse momentum of the quark. Z time, because this is the fraction of energy from Z is equal gamma, the energy of the energy of the hadron over gamma star. Okay, so this is the energy of the particle that you detect, which is linked then to the transverse momentum that you have in the final state of your quark. So, and you measure this PT, which is a combination of this transverse momentum, and involves actually the hadronization process, as Alberto was saying.
Okay, thank you.
You're welcome.
Okay.
Oh, yes.
So in regards to this polarization transfer stuff at the end here, I was wondering if you could elaborate, or maybe if I just missed it, if you could repeat why exactly these experiments need such high luminosities.
Oh, yeah, because you need such high luminosity because you have a polarimeter in the game. So you have to measure, you have your electrons and you have the polarization of your electrons, which is what it is with the luminosity number of electrons per second in the bunch, right? Then what you measure, you have to measure the polarization of the scattering proton. So you have a proton which is produced with a certain energy at a certain angle, and the cross section for the scattering, I remind you that higher you go in Q square is 1 of the Q squared before. Okay, drops dramatically. In addition, so you have in the final state your proton, but it's not the end of the story because you have to measure the polarization of the proton. What does it mean? This proton has to pass through a polarimeter, which is made of some analyzing material, which has some analyzing power and some tracking before and after the analyzer. And this analyzing power is of the order 10, 15, 20%. So your counts drop dramatically each time that goes to an analyzer. This is why you need high luminosity. You cannot do with a low luminosity.
Thank you.
No more question? Okay. So we have a 15 minutes break, and you can have the question while we have the break. And
oh yeah, we can have a break and talk. I mean,
we stretch.
hi,
my question relates to the like the maximum energy that we design for a detector. So when you think of like we'll build a detector which goes up to 6 GeV or 12 GeV or 22 GeV, like what's the bottleneck that stops us from like, going even higher? Like make the electron go one more round around the accelerator and we'll get 24.
okay, higher is the energy, and for instance, higher is the energy, and higher is the momentum and the energy of your final particles. Okay, it means that, for instance, you have a time of flight to measure the momentum. Time of flight cannot go above a certain energy with the resolution that you need. Or you have a rich detector, for instance. In class 12, we have a rich detector that can measure momentum of the particle up to 8 GeV. But if you go to much higher energy, you cannot measure it, and you have particle produce at higher energy, you cannot detect. Or what else? The electromagnetic calorimeters, all the
magnets.
The magnets that cannot be the resolution, exactly, because the rigidity of the magnets is calibrated for a certain energy. And so if you have a very high energy, you know that the curvature depends on the momentum of the particle, right? So if the momentum is very high, the particle is more straight, and you don't have the resolution, enough resolution to measure the momentum of that particle. So all these pieces, You have to find a compromise. Or if you, in fact, with the 22 GV, we are going up in energy double. We have some part of the detector that will work very well, some other, so we have to reduce the phase space for certain reactions. Yeah, but it's
Yeah, and in fact, you cannot bend it back for the next pass because at some point you need a bigger magnet, even in the accelerator, to bend it back and go through again the straight part.
but he was talking not of the magnet of the accelerator, right? We are not talking about the accelerator part, the detector part. You were.
Like I was
Sorry.
talking about what's restricting us at a certain energy,
But for the accelerator or for the detector?
like for the whole thing. So
For
when
the all
it
things, I
like-
mean, you have to ask for the accelerator to accelerator people.
Well,
But
it-
you have
it's
the
how-
magnets, yes,
Basically, how
all
strong the
things.
magnets you need to
Yeah.
bend back the
yes.
electron. So if you go beyond 22 GV, you need even stronger magnet because JLab is built with these two straight tunnels where they are. You cannot move them.
Not only that, then, but if you
There are
have
many.
more, you have a more radiation. So there are many problems. So for each energy, actually, you have to, with the 22 GV, we are still able to do what we need without losing too much.
More questions?
Okay, so I learned that I didn't realize that JLab had one of the highest luminosity detectors that we have up right now. So if I remember correctly, that luminosity has a direct correlation with the cross section. So an increased luminosity is an increased cross section. Is that right or no?
The number of particles in the final state is equal the luminosity times the cross section.
I see.
So the cross section is something independent. There are some, it depends on the process, the cross section.
Okay.
It's not at the machine.
Yeah.
The number of particles very simple. If you want to measure the particle n in the final states, this is just the cross section times the luminosity.
Okay.
So
So,
in the luminosity here, we have your target, you have your beam, practically.
so what are the limits that limit our ability to access higher luminosities?
Oh, okay. First of all, the beam, because luminosity, as I said, target and beam. So it's mainly, it's the beam.
What aspect of the thing?
Oh, I mean, for instance, for AC, they have to reach a certain luminosity, building a very strong hadron cooling.
Okay.
Right, because if you increase of what do you need is that your beam doesn't lose the characteristic of the good characteristic of the beam, so will not become wide because you need for your experiment. What is important is the precision of the beam that you use. It means the resolution in energy, the spread in momentum, the spread in space spread, and if you have in this beam a particle that goes in this way because the multiple scattering, intrabeam scattering, you need a system to re-put all the particles together to increase the luminosity. Because if you have, it's very simple to understand. Imagine that this is your target or even a colliding beam. Actually, this is the example for the AC. It's very simple because they are using the gravity technique in order to increase the luminosity also. Because if you have a head-on beam interaction, and this is your beam are like this, and your particle are inside this beam, and you have head-on and on scattering, you have a small area here that interact. But if you put your beam like this, that interact in this way, this is the area that you are going to use. And this is the technique, for instance, the AC that are going to use to increase the luminosity.
So they have higher strength, quadruple magnets that will
Yeah, I think this is accelerator.
Oh, okay.
It's not my expertise. I'm sorry. I cannot say anything.
Okay, so now breaks and we come back in 15 minutes.
And the coffee machine have reappeared together with cake. So